Let us revisit this calculation of x to the power n. I'm now going to show you a much more efficient way of doing this calculation. So I'm going to assume that x is not 0. And we already have these two cases. When n is 0, x to the power n is defined as 1. And when n is negative, we have a formula for calculating x to the power n. So if n is positive, we can actually break this into two subcases: even positive numbers and odd positive numbers. And we can replace the old inductive definition of x to the power n with these new definitions. So when n is even and a positive number, x to the power n is defined as x to the power n by 2 whole square. Since n is even, dividing n by 2 will still result in an integer, and so I can calculate x to the power that integer and then just square that. And if n is odd, I have a slightly uglier expression, but since n is odd, n minus 1 is even, so it's okay to divide that by 2 and still get an integer. And then once again, using the properties of mathematics, this definition works out. Now, why am I making these more complicated definitions? So to illustrate this, let me show you two ways of calculating x to the power 1000. So on the left, I'm going to think about all the recursive calls that my old power function would have made using the earlier mathematical definition. And on the right, I'm showing you the calls that this power function will make using the new definition if we implement it correctly. So we know that if we call the power function with the arguments x and 1000, then it's going to make a recursive call in the old case to x, 999, one less. But in the new code, since 1000 is an even number, the next recursive call can actually be to x, 500, and then whatever that is, we will square it. So this seems like a big improvement, but it gets better. What happens in the next step? Well, the old code would call it with 998, but since 500 is even, we can halve that again to 250. 250 is even, so the code on the right would now call make the recursive call with the second argument 125. 125 is odd, so 1 less than 125 is 124, and half of that is 62. 62 is even, so half of that is 31. 31 is odd, so we call 15. 15 is odd, so we call 7. 7 is odd, so we call 3. 3 is odd, we call 1. 1 is odd, so we call 0. And we're down to the base case for the code on the right. And the code on the left, the old code, is still trying to calculate x to the power 990, and it has a long way to go. So this is an example of how a clever definition could result in a much faster implementation. So I'm going to show you the implementation, but I'm going to show you a buggy implementation, and I want you to think about what is wrong with it. Now, the code is a little bit complicated, so I'm going to actually end this video on this point and ask you to reflect on what is wrong with this code. Why is this not a good implementation of the mathematical definition we have on the left? And we'll pick up the discussion in the next lecture.